Problem 62.
Yeah.
Let's start with 62 just because I know I have a student from the other class that wants that one. They weren't here, so let me get that one out of the way, and then we can go to 65, 66, and
Where's
another
that
one.
student?
Somebody that's gone for music. There's a lot of people that want it. And they asked last hour, but I didn't happen to be videoing, so now that I am, let's make sure I get it down. So limit as x approaches 0 of tangent squared x over x. Now, we proved two special trig limits using the squeeze theorem on Friday. We didn't do the full-blown algebraic proof, but we did kind of a proof by picture and intuitive approach to the proof. Just do we understand what the squeeze theorem is saying? And we proved these two. We proved the limit as x approaches 0 of sine x over x is what?
1.
You got it memorized?
No.
Okay, good. You need it memorized. And we also proved that the limit as x approaches 0 of 1 minus cosine x over x is equal to what?
0.
I don't know why my board's jumpy, but it is. And let me just illustrate the proof. If you're thinking about this one, when you plug 0 in to the top, you get sine of 0 is what? 0 in the unit circle, that's 0, and you get 0 in the denominator, so you get 0 over 0, so we know it's a whole, right? Because if it was just 0 on bottom, it's a what? It's a vertical asymptote. But 0 on top and bottom indicates to us that this is a whole. So if you look at this graph, sine x over x, if you remember this from Friday, remember it was a whole at 0, 1, okay? And then what happened is it looked something like this. Called it, does anybody remember that new name that I gave to it? The handlebars, okay? Or your handlebar mustache kind of looking thing. And we can look at the graph, and it's obvious that the limit's 1, right? I mean, it's clearly obvious the limit's 1, and you construct a table of values, you'll see that this approaches 1 from the left and right. That's not too hard to see. But algebraically, the way it's done, there is an algebraic proof to it, showing you how you can do this, is imagining if you had a parabola here, x squared plus 1, and a parabola here, negative x squared plus 1, where the point is defined on both of those parabolas at 0, 1, right? So you have that red dot there. Now on the black one, it was open. Okay? You have that red filling in kind of that open circle. And what happened with the squeeze theorem, it said if you had, considered two other functions where one of those functions, let's call that g, is above f, and then h is below f, what happens is f gets sandwiched or squeezed in between those two at that point. And those 2 points land, and somebody said, well, how close are they? It's actually at that hole. I mean, this is peanut butter and jelly, man. You put the peanut butter and the jelly together, all right? They're all touching, all right? My peanut butter and my jelly touch, okay? And the sandwich bread. They're all together now. They're sandwiched together. It's all together now. So, and because the limit of g is that point, and the limit of h is that point, then f has to take on that limit value, because it's getting squeezed between those two functions. That's what the squeeze theorem is saying. And so we proved that sandwich theorem and squeeze theorem, it's just two names for it, sandwich or squeeze, whatever you call it, proves that this limit value is 1.
So with drawing that graph out on the calc exam,
You don't have to prove squeeze theorem.
no, you don't.
Never. You just need to know these two that were proved by somebody smart, with really, really smart, proved. And it's not that you can't do this time. I just don't waste my time doing it because they don't ask you to do it.
Well, they don't.
No. You just need to know those two facts and know where it came from. Know it. Hey, by squeeze theorem, it's this. So when you go to a problem like 62 now, what you're trying to do is you're trying to create a situation similar to this. You're not going to get the exact same situation, but you're trying to create a situation similar to it. It's almost like doing a proof, but it's not the same thing because I don't want you to misinterpret it and saying, we're going to get it to equal this, because that's not necessarily the case. We're going to get it to maybe part of the problem to be equal to that, but not the whole thing. Part of it might equal sine x over x, but there might be some other leftover stuff. Okay, when a proof, it was just absolutely identical. This equals this. Okay. So how can I get this to look like one of these? Because when I have this, I know that's going to be 1, and when I have this, I know that's going to be 0. And this only works when you have the limit as x approaches what? It's just proved at 0. Anywhere else, direct substitution would have worked. The only problem is 0. Anything else doesn't matter. Okay? So how would you start this one out? Well, what would you do?
Set to sine squared over cosine squared.
That's what I would do. I'd go limit as x approaches 0, tangent squared. I'm going to rewrite it using a trig identity, the quotient identity. I'm going to go sine squared x over cosine squared x divided by x. Okay, what do you do next?
You change.
You could, but I don't know if you would want to do that. It's not saying you can't. I just think you're going to run into a dead end there. I think it's going to be a lot easier to get this than it is going to be to get this. And I don't even know if you can get this. Okay? In fact, I know you can't. I'll just go ahead and say it. You can't get this time. Usually, unless there's addition and subtraction in the problem, I wouldn't introduce it. Okay? If there's no addition and subtraction, we're probably going to the sine x over x problem part. What you can do, there is algebra you can do. What algebra can you do? Yeah, just multiply by reciprocal to the denominator. You can take and rearrange this problem just a little bit. I mean, it's not much. And you can say, okay, this is really sine squared x over cosine squared x. Come on, we're being so jumpy. Times the reciprocal of the denominator. Now, the reason that helps you is because now I'm getting really, really close to getting this. I can split sine squared. Sine squared is really sine times sine, so I can leave one of the sines above the cosine squared and put the other one above the x. Do you see it? Okay, let me write it, and then it'll be like, it'll literally be slapped to your forehead. Here we go, limit as x approaches 0. All right, sine squared x is really sine x times sine x, so I'll leave one of the sine x in this fraction, and the reason you can do this is because multiplication is commutative.
So
You can rearrange the order.
Distribute the cosine squared either.
Huh?
You don't have to distribute the cosine squared.
No, I just leave that alone because I'm trying to get sine x over x. So I wouldn't even bother with the cosine. I'll talk about what we have to do with it in a minute.
Oh, that's just more.
Nah.
Yeah.
See? Now you see it. Now this right here, you're like, okay, limit of a product, I can do the limit of this, and I can do the limit of this. Now, I got this, so I know the limit as x approaches 0 of sine x over x is what? So I know, hey, this is going to 1 now, which got rid of the dumb x in the denominator that was initially the problem. That was the whole problem, was that dumb x in the denominator. Now, I'm willing to bet direct substitution works. Try it. Plug 0 on top, you're going to get what?
0.
That's fine. I don't care about 0 on top. It's the bottom I care about. What's cosine of 0? What's 1 squared? What's 0 divided by anything? 0. So 0 times 1 is what? So you have 0 times 1, which is just 0. That's how you do it. It takes a little bit of work to get to it. That's why I want to do a few of them, so you just get used to the feel of it. It's very similar to knowing identities. Okay, another one.
66.
66, he says. The man says 66. All right, what does 66 say, Canyon?
The limit as x approaches pi over 4.
The limit as x approaches pi over 4.
Of 1 minus tangent x.
Oh, you picked an interesting one. Over sine minus cosine, right? Yeah, I did this last hour. Now, just because I give you these special limits doesn't mean you need them. Okay? In fact, you might not use them, which obviously is a hint here. Okay? Now, here's what you'll try. You'll look at it and say, okay, let's try. What should we always try first? All right, let's try direct substitution because maybe it works. What's sine of pi over 4? Faster.
2 over 2.
Root 2 over 2 minus cosine of pi over 4. So you got root 2 over 2 minus root 2 over 2. What's root 2 over 2 minus root 2 over 2? You got 0 on bottom. That's problematic. Okay? Top. Let's see if we get 0 on top. 1 minus tangent of pi over 4. What's tangent of pi over 4? 0. No.
It's going to be 0.
Okay, that's going to be 1, and what's 1 minus 1? So we get 0 over 0. So, here's your options. There's either some algebra you can do it, there's some factor cancel, there's some simplifying, there's a conjugate possibility, there's some fraction possibility type stuff we could do, or we're going to have to use squeeze theorem stuff. So don't rule out algebra yet, because we got our simplifying. We got our factor cancel. We got our conjugate. We got our simplifying fraction stuff. We got all our algebra. Let's just say all algebra stuff we can do. Plus, now we have this. Okay? Now, is there anything, if there's nothing we can do, then we're going to have to try and do this. But is there any algebra you can do, first of all, that might be helpful here?
Top left tangent.
I can change tangent into what?
Sine.
And I've always told you to do that. If you don't know what to do, change everything to sine and cosine, and let's see what happens. Okay? So we're going to have limit as x approaches pi over 4. Thank you, board. 1 minus sine x over cosine x divided by sine x minus cosine x. Now, why is that helpful? Because I just used an identity. What do you usually do after you do an identity? You do some what now?
Rearrange.
You do some algebra, you do some rearranging, you do some simplifying, you do some clearing out fractions, you do some stuff. So what kind of stuff do we want to do right now?
Move cosine down to the bottom.
I wouldn't do that.
Sine common cosine.
Not multiply by reciprocal, but multiply by the common denominator. Okay? So I want to clear the fraction out. See, I don't like this fraction on top. Do you? So what do we multiply top and bottom by?
Cosine.
Cosine. That might be what you've been thinking and you just called it something else. Is that what you're kind of thinking? That's why you're thinking by cosine. Okay? So it's multiplying by the least common denominator. It's clearing the fraction. So now we get the limit. This falls right out too now. You're going to be like amazed. Okay? What do you get here? Cosine. Minus, what do you get here? Sine. Bottom, you're going to get cosine x times sine x minus cosine x. And some people are like, why do you never multiply the bottom out? Because factoring something factored is usually more simplified in calc than it is multiplied out. It's better to have it factored than it is to have it multiplied out usually. Now on top, the reason I multiplied it through is because I specifically wanted to get rid of that fraction. That's the only reason I multiplied it through on top, because the fraction's more complicated. Now, what do you see? What do you see? This was a factor cancel problem. Look at it. It came up on the quiz on Friday that some of you still haven't taken. Can I cancel those?
Yes.
Yes, you may. But how do you cancel them? Because they're not exactly the same.
Negative 1.
Nope, they cancel perfectly. It's sine minus cosine, cosine. But it gives you a negative 1. It's good, you guys are thinking. You get everything right yet? So it's negative 1. They're identical. It's cosine, negative sign, positive sign. So they're different by a negative. So we got negative 1 over cosine x. Now, that was originally the problem. We got rid of the problem. Try direct substitution again. What's cosine of pi over 4? Root 2 over 2. What's the reciprocal of root 2 over 2? So the answer is negative root 2. Did not need the squeeze theorem on this one. Squeezing theorem. Okay, another one. Got about 5 minutes I can answer questions for. What else?
61.
61. What does it say?
Limit as x approaches 0, sine squared x
Over what?
over x.
Oh, you really want this one? So we basically did this already.
I figured we did.
Because you split it and go sine x over x, and you have sine times sine x. Let's don't do that one.
65.
65. What does it say? Does that make sense now? It's kind of like the tangent squared x over x. In fact, you get that in the second part of the problem. What is it?
Limit as x approaches pi over 2
Okay?
of cosine x over cotangent x.
Cosine x over cotangent x?
Yeah.
That's basically the same thing as the last one. Change cotangent and cosine over sine. Let's do another one.
Do 67 or 60.
You get that one?
Yeah.
Do you want me to? I'll get it. Make sure you know what I'm talking about here. Change cotangent into what? Cosine over sine. Then multiply by the what? That one you do, well, this one's actually reciprocal this time. Keep your reciprocal straight and your least common denominator straight. Which one's which? So we're going to go cosine x times what? Sine x over cosine x. Do you even need a squeeze theorem on this one?
Just sine.
Or X substitution.
Pi over 2 would be what? 1. What else?
68.
What's 68?
Limit as x approaches 0. Sine of, well, never mind.
The answer's 2/3.
Yeah.
Let me show you why, though. I don't think you'll see why on this one. Okay, what is the original
Well,
problem?
you told us. Never mind.
You might want to see this one, how I get to 2/3, even though you can look at it and see it. Sine of what?
2x over 6.
Okay, this will give it away. You see this right here? It also works like this. It has to be of the form sine x over x. It also can be of the
Oh, we went
form.
over that on Friday, though, I think.
Yep. It also can be of this form. Its reciprocal also works. If you don't believe me, use a calculator, check it.
Is that the same for the other two?
Huh?
Is that the same for the 1 minus cosine?
No, not the same for that one. But it is for this one. And it's just because it equals 1. That's why. And here's what happens on this one is, and if you think about it, it's because the reciprocal of 1 is what? 1. That's why. Reciprocal of 0 is not 0. Reciprocal of 0 is undefined. Okay? So this works here. So it's of that form, and yes, he's right. We did that on Friday. As long as whatever's here and here is exactly the same. So it can be sine 2x over 2x. It doesn't matter. You don't know what x is anyways. Who cares if I double it? If I double it on top and bottom, it doesn't matter. We don't even know what x is to begin with. We can just call it big X. So if you get 2x and say, I don't know what that is, let's just call it big X. You can have 10x, be like, who cares? Let's just call it big X. It's bigger than the x before. Okay? Somebody be like, well, what if you go 1/5 x? Well, then you can call it little x. Okay? Not that you would know it was negative or positive anyway, so it's really ambiguity all over the place. All right, so here's what you can do, though. I want to get sine 2x over what? Over 2x. Okay? So what I'm going to do is I'm going to kind of split it. I'll show a lot of work here, even though I don't need to. I know the answer. The answer is 2/3. You should just be able to look at it and see it's 2/3. But here's why. You get sine 2x. So let's just kind of look at that first. And then I'm going to look at the other part. 1 over sine 3x. Now watch what happens here. So just kind of split it. And then for the first one, you'll say, okay, I need a 2x on bottom. So if I need a 2x on bottom, I need to multiply top and bottom by 2x. Agree? Here, I need a 3x on top. Do that. So then you get the limit as x approaches 0 of 2x times sine 2x over 2x. You with me? Times 3x over 3x sine 3x. Are you with me? Now, what does this equal? 1. What does this equal? 1. So now you're down to limit as x approaches 0 of 2x over 3x because these guys went to 1 because of squeeze theorem. Now you're like, okay, try direct substitution, but you get 0 over 0. That's fine. Cancel the dumb x's out. Now it works. Limit of a constant to what? That's why it's 2/3. Okay? Any questions?
3x over sine of 3x goes to 1.
Because I said the reciprocal works, because the reciprocal 1's 1. If you reciprocate the handlebar function, everything flips around. Kind of like, remember when we did cosine, we did the reciprocal, everything flipped? Remember when we learned how to graph cosecant and secant, we reciprocated sine and cosine?
Yeah.
So the got a hat up, hat down, but at 1, it stayed 1. The negative 1, it stayed negative 1, because the reciprocal 1 and negative 1 stayed 1. Okay. All right, go to Moodle.
Tell me when period 5 starts. Like what time does it start?
Period 5. What period are we in now?
I mean, it's at 105.